Hello and welcome to the first in our series of analytical insight videos where we bring you expert advice on how to improve the quality and reliability of your analysis and help you reduce costs and wastage in the process. Today's labs play a key but often unrecognised role in our everyday lives. They analyse samples that help authorities check that the air we breathe meets quality standards, that the food we eat is exactly what it says on the label, and to help develop the latest pharmaceutical and chemical products for our ever-advancing world. Not to mention a whole host of other vital everyday tasks. So it's essential that labs are more accurate, more precise, more reliable, faster, safer, and of course, more cost-effective than ever before. And that means that analytical chemists need to find new ways of continually improving their processes. A trend we've seen recently in gas chromatography is the use of hydrogen as a carrier gas. There have been some concerns regarding the long-term availability of helium, which has led to much discussion in the analytical press. As one of the global leaders in the supply of ultra-high purity gases, Air Products can give a truly informed view of the helium supply situation, as well as an independent view of the merits of hydrogen as a carrier gas, with the support of our partners in the analytical segment. I hope you find the video interesting and informative.
Since the original development of gas chromatography, many chromatographers have believed that hydrogen is the best carrier gas for GC analysis. In many applications, hydrogen can be the carrier gas of choice because of the combination of fast analysis, high efficiency, and reduced costs. However, helium is still by far the most commonly used carrier gas because it is inert and non-flammable and possesses physical properties that permit fast, high-resolution, temperature-programmed gas chromatography. As one of the global leaders in helium supply, Air Products estimates that at today's demand level, known helium reserves will last for approximately 300 years. When new helium reserves come on stream, world supply will exceed expected demand. The recent temporary supply shortages have prompted some chromatographers to re-examine the benefits of hydrogen as an alternative carrier gas. Although hydrogen is flammable, its high diffusivity allows faster linear velocities and consequent shorter analysis times, with typically the same separation efficiency that is provided by helium. In this video, we will review the different carrier gases used in gas chromatography, the purity requirements for hydrogen, and the different modes of supply. We will compare the cylinders that are most frequently used in laboratories with hydrogen generators. For example, in these chromatograms using the same column and conditions, you can see the differences using hydrogen, helium, and nitrogen as carrier gases in temperature-programmed capillary GC. Notice the differences in the retention times and resolution. Faster analyses translate into increased throughput, which means lower cost per sample. In some situations, reactivity could be a problem when using hydrogen as the mobile phase. An example is the catalytic hydrogenation of unsaturated hydrocarbons under certain conditions. The potential for chemical reactions in your analytical system must be considered. There are also some issues in using hydrogen as the mobile phase in GCMS. Speak to your GC supplier for advice. Responding to the increased interest in hydrogen as a carrier gas, Air Products has undertaken extensive research on alternative methods of providing a consistent, ultra-high purity source of hydrogen that will be perfect for modern high-precision gas chromatography. The best solution currently on the market is the hydrogen BIP cylinder. Besides being filled with ultra-high purity hydrogen, there is an internal purifier system and unique valve design that achieves ultra-low impurity specifications that are not possible from any other technology. It's not only about changing to hydrogen, but about selecting the right quality of hydrogen. In this table, you can clearly see that the critical impurities of oxygen, water, and hydrocarbons are up to 100 times lower in hydrogen BIP than in conventional hydrogen 5.0, the most common purity used in laboratories worldwide. These specifications for hydrogen BIP make it the perfect choice both as a fuel and carrier gas. This chromatogram shows the typical results for GCFID when using hydrogen BIP both as a fuel and carrier gas compared with using hydrogen technical grade. You can see the difference between using the different purities of hydrogen, both in terms of baseline noise and column bleed. Hydrogen generators offer an alternative supply option for GC carrier and fuel gases, and we will now consider their relative advantages and disadvantages against cylinders. First, the advantages. They are a good solution in extremely remote locations where cylinder supply is difficult or impossible. They produce hydrogen on demand, so little hydrogen is stored. They operate at low pressures and do not require high pressure regulators. The disadvantages of hydrogen generators are hydrogen generators are usually much more expensive than hydrogen cylinder supply. Even the best hydrogen generators can fail catastrophically without any warning, so backup cylinder supply is strongly recommended. Many hydrogen generators are not suitable for gas chromatography. Before purchasing, the generator specifications must be checked carefully. Most manufacturers only give either the oxygen or water impurity levels, not both. Deionizer bags purify the demineralized water supply. These must be changed often, as recommended by the manufacturer, or the generator will be severely damaged. In summary, hydrogen can be successfully used as a carrier gas in gas chromatography to give fast and accurate analyses. However, helium continues to be the carrier gas of choice for most chromatographers because it is inert and non-flammable and permits high resolution, temperature programmed gas chromatography.
At Agilent Technologies, we know the challenges chromatographers face today. That's why we develop new products to make their work easier with features that will help to produce faster, reliable, accurate, and cost-effective results in traditional labs or whenever mobility is required. Which is the best carrier gas to achieve those objectives? Around 90% of the existing GC instruments run with helium as carrier gas. Some people still use nitrogen, probably because it was installed this way when they work with packed columns. However, some people have already started to enjoy the benefits of using hydrogen as carrier gas in their GCs. Does the choice of the carrier gas interfere with the chromatography process? Yes, it does, through its diffusivity and viscosity properties. You have certainly seen the so-called Van Dinter curves, plotting plate height against gas velocity, where the optimum gas velocity is at the lowest point of the curve. The larger the plate height, the worse the separation. Do you want to know why hydrogen is the best carrier gas? Hydrogen has the widest flow range, so fast analysis is possible. It is much cheaper than helium, and besides GC, it can also be used with MS systems. By changing to hydrogen, we not only benefit from faster analysis, but we also benefit from a higher response. As the peaks elute faster, the height of the peaks will also be higher. For a similar signal to noise, one can inject half of the sample, from which we can benefit in less contamination of the system. The pressures for using hydrogen are the same as we use with helium. Due to the lower hydrogen viscosity, we can get approximately double linear velocity. That's why hydrogen is the preferred gas, for instance, when using GC-GC MSD with microfluidics technology and dual thermal mass external ovens. Nitrogen is still used in many packed columns applications, as it is very cheap and can also do the required job for an easy application or when helium is not available or hydrogen is not an option. Helium is as good as hydrogen if inlet pressures are below about 50 kilopascals, but requires slower GC at higher inlet pressures when using longer columns, being the difference roughly a factor of 2 when above 150 kilopascals must be applied for helium. Some safety and proper use considerations need to be implemented when switching from helium to hydrogen, and more specifically when AMS detector is in place. Our challenge as analytical chemists is to do this conversion without altering performance criteria. Time should be allotted for adapting the method, optimization, and resolving potential hardware problems. Some areas will need your attention. You should consider to choose the proper column dimensions and the correct analytical conditions. The quality of the gas is key for success. Sourced by a cylinder or a gas generator, make sure you get a good one with a low specs for water and oxygen and assuming a consistent purity over time. You should consider changing the pipe with chromatographic quality stainless steel tubing for cleanliness and safety. Consider the GC/MS required hardware changes according to manufacturer instructions. Choose the right chromatographic conditions. You can obtain the optimized method parameters fast and easily using free applications such as the Agilent Flow Calculator and Method Translator. Besides the intrinsic safety of the GCs, when connecting a hydrogen source of GC, we recommend to install an integrated hydrogen sensor. It will switch automatically to an inert carrier in case of detecting a potential explosive atmosphere in the GC oven. Some hydrogen generators have these safety features already in place, so they stop generating hydrogen if a leak in the GC oven is detected. There are new features also implemented to save gas consumption and electricity in modern GCs, as the Agilent 7890B sleep-wake modes of operation that reduce the gas consumption by changing automatically to a cheaper carrier gas while the GC is in the idle status. There will be some issues when specifically switching GC/MS methods to hydrogen. Most of them can be minimized with proper instrument setup and conditioning steps. Mainly, all new GCs and MSDs instruments from principal manufacturers are designed nowadays for its safe use with hydrogen. Some of these features will be presented later by Dr. Lourdes Vega from MatGas. In summary, the technology is completely ready for the labs to use hydrogen for the analysis in a safe, reliable, and cost-effective way.
The modifications required to the gas chromatograph when switching from helium to hydrogen as a carrier gas are related to hazards of hydrogen. Hydrogen is a flammable gas that can create an explosive atmosphere wherever it accumulates. This can be properly addressed by safety standards, ensuring no hydrogen accumulation is possible by avoiding and detecting any leak and safely venting any outlet stream. Modern GCs are able to detect leaks upstream the column by monitoring gas pressure. This can be directly used for a GC working with hydrogen. If hydrogen leaks before reaching the column, the pressure drop of the GC is negligible. Hydrogen pressure cannot build up and reach the defined set point. In this case, the control of the GC interprets the permanent difference between the operative and the set point pressure as a leak and protects the GC by shutting off the hydrogen valve. However, this safeguard cannot be efficient when the leak is downstream the column. In this case, hydrogen sensor needs to be installed to detect any hydrogen accumulation in the oven. Here we have the hydrogen sensor we have installed inside the oven and the switch valve. If the sensor detects hydrogen in the oven, it switches from hydrogen to another inner carrier like helium or nitrogen, avoiding the hydrogen accumulation in the oven and protecting the column by keeping the carrier flow. The second modification is related to safely venting any hydrogen outlet stream. These ports are the outlet of the septum purge and the split from the injector. When helium is used, it can be vented outside the lab. But if hydrogen is used as a carrier gas, these ports need to connect it to the lab's flammable vent line. As our lab was already prepared for work using hydrogen with the supply of the FID detector, no further modifications were required. As you saw, the modification to move from helium to hydrogen as a carrier gas are, in a modern GC, are minimal and safe. When all the hazards related to hydrogen were successfully addressed, we verified the reliability and reproducibility of the new GC configuration versus helium by standard FID performance evaluation tests. This standard consists of separating and detecting 4 different hydrocarbons: C13, C14, C15, and C16. As you can see in this chromatogram, better performance is obtained with hydrogen beep compared to 5 helium for the same samples. The baseline is more stable and accurate. One additional advantage of working with hydrogen as a carrier gas is the possibility to choose between improving the resolution of the analytical procedure or the speed of the sampling time compared to helium to increase the GC productivity. In summary, we are very happy with our decision to move from helium to hydrogen beep for GC. It has allowed us to reduce the cost of using this analytical tool while improving its performance and reliability. As hydrogen hazards has been successfully addressed, we are enjoying the advantages of hydrogen with all the benefits it delivers.
I hope you found these insights useful. Assuming hydrogen is used at the right purity and the correct safety measures are taken, hydrogen can be a highly effective carrier gas that can improve quality, speed up your process, and help you save money. Thank you for watching, and do look out for more expert insights in our next video.